working on QML and QML tooling for a while, I am going to talk a bit about the new Qt Quick Compiler technology. New Qt Quick Compiler technology lets you speed up your application by compiling your QML code to C++. If you have any questions, please type them in the chat box during my presentation. I will reply to them after my presentation. So what is this all about? I'm going to give a little overview of the various terms involved, and I will show you how it all fits together. Then I'm going to talk about some numbers, like what speed up can you expect, and yeah. Then I'm going to show how you can adapt your code for best results when compiling QML code to C++. Finally, I'm going to talk about direct mode. Direct mode is a commercial-only feature that you can use to get even faster binding and function evaluations. And in the end, I'm going to show a little roadmap and some pointers to further documentation. So, the Qt Quick Compiler, its current iteration, consists of QML Cache, that's been available since Qt 5.9, it's open source, and it got a major overhaul in Qt 6.3. Since Qt 6.3, it can actually compile functions and bindings to C++, provided they are well behaved. Then there's qmltc. qmltc is also available since Qt 6.3. It's also open source and it can compile your object structure to C++. So it generates a C++ class from your QML document, and you can instantiate that C++ class without using QML component or QQuickView or similar wrappers. In addition to Qt Quick Compiler, there are also the Qt Quick Compiler extensions. The first release of Qt Quick Compiler extensions is compatible with Qt 6.2. It's commercial only, and we've released further versions of the extensions with each Qt release, compatible with each Qt release. What it does is it replaces QML Cache with a different compiler called qmlsc, which comes with some extensions. In particular, it supports direct mode. Direct mode, I will go into details later, allows you to directly call into the C++ classes underlying your QML types, and therefore allows faster execution of bindings. So you might have heard the term Qt Quick Compiler before, and in order to clear up some confusion around this term, I will give some overview of the history. The first time we've used this term was with Qt 5.3. There was a QML compiler that had a primitive native code generator that's basically remote controlled the QML engine and had similar generic type system as JavaScript itself. With that concept, it couldn't really generate much better code than the JIT could. So eventually, the JIT surpassed the performance of the code such generated, and QML compiler was dropped. In Qt 5.9, QML Cache was introduced. QML Cache, however, does not really generate native code. It generates the same bytecode we use nowadays to feed the interpreter and to generate native code by using the JIT. So what it does is it optimizes the compilation step, not the evaluation step. By using QML Cache, you can generate the bytecode ahead of time at the compilation step of your application rather than at runtime. This is nice, but it doesn't really make the evaluation of bindings and functions faster. In Qt6, we picked up the very first approach again and said, okay, we actually want a native code generator. And what was missing in the old QML compiler was obviously the information about the types involved when evaluating a function. So we pass some arguments to a function, and in JavaScript you just write function braces a, and that a could be just anything. So we set up an infrastructure to pass the available type information around at compile time rather than at runtime, and with that at hand we can actually generate better code than the JIT can. The new approach still retains the functionality of old QML Cache, so we still generate bytecode and you can still interpret the bytecode or run that with JIT, but in addition we also generate native code for the functions that are suitable for that. Plus, there's a separate compiler to optimize the object creation. That is, qmltc creates a class for a QML document that you can directly instantiate. So with that out of the way, let's look at how the different compilers actually work. So this is about the old QML Cache before the major overhaul in Qt 6.3. What you can see here is we are starting with this QML file. We can either, as we could have always been able to, load it at runtime, then get a compilation unit in memory, then interpret it or run that through the JIT, and there we go. That has the downside of this step, which is very noticeable in most applications. Now with QML Cache, we can also instead compile the QML file ahead of time into a bytecode that is then bundled into the compilation unit in the binary, and the QML engine will just load that bytecode and interpret or JIT it right away. So this saves you the compilation step at runtime, which makes loading of most applications faster. Back then, we didn't call it compilation, we called it QML caching for historical reasons that I'm not going to go into right now. Contrast that to the new approach in Qt 6. You can still see the old paths here. We can still take the QML file, load it at runtime, get a compilation unit in memory, etc. You can also still get the bytecode, bundle it in the binary, and interpret or JIT it. But in addition, after generating the bytecode, we look at the functions again and see, some of them are well behaved. We can generate C++ code for those. The C++ compiler can compile that to native code, which is also integrated in the binary. And then it can call those functions directly rather than interpreting or JITting them. And those direct calls are faster than the interpretation or the JIT step. And that has been available either with the Qt Quick Compiler extensions or with QML Cache from Qt 6.3. Finally, there is the object creation compiler, qmltc. So what you see here is again our QML files. You can load them at runtime and instantiate them via interpretation. So you use QML Component or QML Application Engine, QQuick View, there are a couple of those. And those look at actually the compilation unit but let's forget about that for now and instantiate the QML component as Q objects. Now, this interpretation has a cost. So qmltc looks at that and sees, we can compile that ahead of time, and it generates a header in the C++ file for each component. You can include that into your main CPP or anywhere, and you can just instantiate the resulting class in your application. So what happens is the C++ compiler compiles this generated C++ file, and that becomes part of your application, and there you go. Now, what does it give us? As said before, QML Cache allows the compilation to bytecode to be skipped at runtime. Okay, we know that already. We've seen numbers about that several times. I'm not going to go into details on that. What I'm going to show is how much faster the execution of bindings and functions is when precompiled to C++. What I'm also going to show is what qmltc does when you instantiate a component. On the one hand via QML component, and on the other hand via just creating the object from the generated class. And in addition, I'm also going to show the Quick Compiler extensions and how much additional speed up that gives you in comparison to what QML Cache does. So here, those are some like real-world bindings I've been profiling, and let's first take a look at those documents here. So the bindings one here, this one, is basically this binding. So we have a lookup by ID and then a lookup of a property relative to that ID, then some arithmetics and another lookup. What we can see here, we get a pretty nice speed up. This is the JIT. Then the indirect mode is what QML Cache does, and direct mode is what the extensions do when using direct mode. The second document here is this one. There you have similar bindings, some arithmetics, some ID lookup, some property lookup, but also some context lookup. This is a lookup of a property in the context. We see, okay, the context lookup apparently makes this much more beneficial to use the compilers. Then finally, the third one is this one. The difference here is that we have a procedural assignment of a property, and some of the stuff we've had before. This procedural assignment is much faster. Then the last one is basically just more of everything. So what we can see from those numbers is, in general, you can get up to 25% speed up in indirect mode and up to 33% speed up in direct mode. However, what we can also see, the exact results depend heavily on the specific workload. For example, our width and height properties there are qproperty. Properties implemented with qproperty rather than getter, setter, and notify signal benefit especially from direct mode. Then what we haven't seen here is enum lookup, but enum lookup is easily optimized, and you get much faster evaluation for enum lookups. Then, for example, creation of value types list is much faster, and math functions get inline generate code. However, many JavaScript constructs cannot be optimized at all so far. So there's upsides and downsides. However, if a function cannot be optimized, you still get the bytecode and you still get the old JIT performance. So it's not too bad. The object creation compiler, I've used a medium large document here to show this off. What we are doing here is first on reload, we recreate the QML component in each iteration. So I create a QML component, I create an object from that QML component, then I throw it away and redo it, and I benchmark that. In recreate mode, here the gray bar, we use the same QML component in each iteration. So I create a QML component with a URL. Then I repeatedly create objects from that without throwing away the component. And qmltc is, okay, I don't use the QML component again at all. I just instantiate the class qmltc as generated for me. So what we can see is in the qmltc case, we get a around 40% speed up in this case. However, again, this heavily depends on the specific workload. Why did I make the difference between reload and recreate here? Well, there are some components that you will load only once. For example, the root or entry point of your application. There it makes sense to count the creation of the QML component in the total cost of the creation of the object. And there are some components you may create over and over. For example, some delegate in a model, some delegate in a view that's based on some model. And there you can reuse the same component, and it doesn't make sense to count that into the cost of creating the object. So as we can see, using the compilation to C++ can have great benefits to the performance of your code. And so let's see how we can help the compiler generate the best code for your application. First, how does QML Cache actually work? The compiler workflow, as we've seen in the picture before, is first it generates bytecode for all functions and bindings, and that bytecode is always available as fallback. Then it collects type information from the QML document and its imports. It then processes each binding of function and propagates the type information through the function. So basically for each variable, parameter, return statement, or anything you do in the function, it tries to determine, okay, what type is that? Is it a integer? Is that a string? Is that some date or whatever you may be using, a list? And if it figures out, okay, I don't know what this is, then it has to skip the function. However, if at each point for each register it can figure out, okay, I know what this type is, then it continues. It performs optimizations and drops that code in that stores. This is surprisingly significant. And then it tries to generate efficient code for each instruction. If we can't generate code that's more efficient than what the JIT would do, we skip the whole function, because we cannot guarantee then that our compilation to C++ would actually be better. And the result is then compiled into the application binary. So, first thing you have to do in order to help there is you have to make all type information available. As obviously, that's the first thing it does. It propagates the type information. Where does it get the type information from? Well, the types exported from C++ need to be visible at compile time. That is done by annotating them with QML element and similar macros. And note there is QML foreign that you can use if you cannot change the type itself but still want to make it available. So let's look at an example. I have here my example application. It comes with a couple C++ types, or actually one for now. This is my type. It has a property and some signals and setters and getters, and I just write QML element. And that's the most important thing. Once that is there, we can see it at compile time. What I do not do is write QML register type here. Nope, I don't do that. Because if I did write QML register type in the main function, the mock would have no chance of seeing, okay, this class is actually supposed to be exposed to C++. And so we wouldn't see it at compile time, and we couldn't propagate its type information anywhere. In order to actually propagate the type information to the compiler, and in order to make sure the compiler is actually used, you have to use qt-add-qml module in CMake. So let's also look at that. Here I'm saying, okay, this example here is a QML module. It has a URI, it has a version, it has a bunch of QML files. And this is important. You add the QML files as part of the QML module. Only then can they be compiled to C++, and only then can we see that those are actually also types that might be used somewhere else in QML code. What we don't do is qt-add resources. Nope, I don't do qt-add resources with those QML files here. No, because resources can be anything, and we've decided that resources will be disregarded. Plus, if you have more than one module, you have to make sure that all your modules can be found. You can set up an import path. Yeah, I'm not going to go into details on that, but the most important and simplest way to make your modules available is to place them relative to the application. So let's look at another example. I have this extra module here, and I add a subdirectory called extra. And in that subdirectory, I add another QML module. And the crucial thing is the URI has to be the same as the name of the subdirectory. Then the QML compiler will find this module relative to the application and will be able to see this extra QML here as an extra type that can be used in our main QML here, as we actually do extra. So I can compile that, and it just works. Then let's look at this again. Once we know all the type information, we have to make our code understandable, so that the compiler can actually generate efficient code from it. How do we do that? First, we have to add type annotations to all our functions. So let's look at the example again. We have a function here, do thing, and since Qt 5.14, you can add those type annotations. You can say, okay, this parameter a is actually an int, and what we want to return is also an int. And then this addition here makes sense for the compiler. Now it knows, okay, there's an integer addition. We can generate very good code for that. If we hadn't annotated our parameter could be anything, and anything can be coerced to string, for example, and that would make some interesting code here, because we wouldn't really know what code we would have to generate for that addition. It would depend on the actual parameter passed in, and we would have to switch over lots of different types to figure this out. We don't want to do that, as that's inefficient. So we add type annotations to all functions. Second, we avoid context properties. What we can see here is we have the singleton, or we have some parameter s that we want to pass in that should be the same everywhere and should be available everywhere. The classic way to do that would be engine root context set context property, etc. That's how we did that in Qt 5, right? The problem is we can't see this context property at compile time. No way. Because you can add context properties to just about any context in just about any engine, and yeah, we don't even know where to look there. And the same QML document can be loaded with different context properties available. So this is like out of scope for the compiler. Instead, in most cases, we can use singletons. So how do we define singleton? First, we write pragma singleton in the QML file, and second, we add a source file property to the QML file called qml singleton type. And then in the singleton we can add any properties we like, and those will be available anywhere. For example, like this. Third, you should not import just Qt quick controls. That's a common thing to do, but since we don't know what Qt quick control style will be loaded at runtime, we cannot generate any efficient code for anything that uses something from Qt quick controls then. Instead, you can, if you want to go that step, import a specific style, for example Qt quick controls fusion. And when importing that specific style, we know what types will be available at runtime, and at compile time we can generate code that accesses those specific types. However, then you cannot configure your application anymore with Qt quick controls conf, etc. It's then bound to that specific style. What you can do is use QML dir imports to select the style depending on platform at compile time. You can look at my blog series for an example of that. Then fourth, what we have to avoid is unqualified access to the properties of the component root, because looking up such unqualified access is rather complicated. So for example, in this extra element, we might be compelled to write just title, because we know window has a title and we can just access it directly without qualification. Yeah, you can, but since pretty much everything else overrides this unqualified lookup, the compiler doesn't really know what's going on there. Like context property could override this, or a new property introduced in some later version of extra could override this. Therefore, the compiler just rejects the lookup of this title. However, you can qualify the lookup. You can say, okay, it's actually the title of the window I want here. And then we know exactly what it is and what type it is, and the compiler will generate the right code for it. Finally, what you should do is use programmer component behavior bound. Why? Well, let's look at inline components. We have one inline component here, an item that has an object name, which is again this title. Now, if we went and instantiated this inline component, inline, in a different context, then this window would not be available, because the ID window is only available in this context here. Therefore, this title would be something totally different, or nothing at all, probably, but who knows what other window you might have in that context. The compiler cannot deal with that, or doesn't want to deal with that, because it's slow. So we've added a way to guarantee that this inline component there is instantiated exactly in the context where it's declared, namely this file. If you write programmer component behavior bound in your QML file, then all component elements, you can also do that, that would also be affected. And all inline components can only be instantiated in the same context, and then we can know that window is actually the window from this context, not something else. And then the compiler can compile this binding. So whenever you use component or inline components, do add programmer component behavior bound. Furthermore, we want to allow efficient code to be generated. One thing to avoid then is calling untyped JavaScript functions. First, you should not add your own untyped JavaScript functions, as we've seen before. But then the JavaScript host environment has a large number of untyped JavaScript functions, and most of them you should not call in code that should be compiled to C++. There are a number of exceptions. First, we've optimized all members of the JavaScript math object. So you can call math functions as much as you like. For each of those, we have an inline variant that will be generated into your code right away. Since math can only be done on numbers anyway, this was easy. Then, string arg and the various translation functions have been optimized in Qt 6.5. So you can also use those nowadays. Other things have not been optimized yet, but there will be more optimizations for other JavaScript globals. In particular, console log will probably be the next one, since it's so common. Then you should not use var properties, for the obvious reason that a var property can hold any type, and we want to know your types ahead of time. As soon as you use a var property, we would have to generate code that switches to all types possible there, and that would be rather expensive. A common problem that was solved by var properties was storing lists. This is not necessary anymore. Nowadays we have list for all the list properties for all value types. You can, for example, write list string and that will be a typed string list. And of course, you can still use list with any object types, like you've always been able to list item or list queued object. Then you should avoid manipulating JavaScript objects, prototypes, properties, etc. This obviously, since all the properties of a JavaScript object are highly dynamic and can be of any type, we cannot say anything about that and won't generate any code from it. However, JavaScript arrays, JavaScript array literals most prominently, can be efficiently converted to QML lists since Qt 6.4. This works by not creating a JavaScript array in the first place, but directly creating the list. That's also why it's much faster in compiled mode than in interpreted mode. And yeah, just like JavaScript objects, prototypes, etc., JavaScript closures and JavaScript new is not really suitable for compilation to C++. With that out of the way, let's look at the object creation compiler. What can you do there? First, what does the compiler do? It collects type information from the QML document and its imports. It analyzes the types of all objects it remembers in the document. If something is missing, it fails. So this gives you a compile error. That's in contrast to QML Cache, which only omits the function and generates no C++ code for it. In qmltc, if you're using qmltc, it will fail. Then it generates a C++ class for each element in the document. QML properties become QProperty, QML functions become QInvocable methods, QML enums become C++ enums, QEnum, etc. And it generates glue code to set up the QML context, bindings, etc. What can you do? Well, make all type information available. We've had that before. That's equally important for both compilers. You need to use QML element, you need to avoid QML register type, you need to use qt-add QML module. You should not add QML.js files as plain resources, and you need to make sure that all your modules can be found. On top of that, you need to use the generated types. First thing to do is enable the type compiler. I've done that in this extra module here. This way we enable the type compiler. That's it. With that added, it will compile this extra QML to C++. Then you need to include the generated header in your C++ files. I've added a little factory here that just creates this type, and what we do is we include extra h here. Our extra h looks a bit messy. We see it's actually generated from this QML file, and what we have here is a class that inherits from QQuickText since it was text and carries a new property. Then we can instantiate the generated class from C++. So new extra. We need to pass a QML engine since we need to set up the bindings, etc. And we might pass a parent. And then we can set properties on it. We can get properties from it, etc. Just like any class in C++. What you should not use for now is QML Component, QQuickView, QML Application Engine, etc. to instantiate the QML types. We're going to add some bridges for those, but the most important way to instantiate the generated classes is via direct inclusion of the headers and direct instantiation. Now let's also take a short look, as we are running out of time, at the Qt Quick Compiler extensions. The Qt Quick Compiler extensions come with an extra mode that's not available in QML Cache. That's direct mode. QML Cache cannot rely on your on the QML modules your document uses to be available as C++ modules, or the QML components that your document uses as C++ classes. So what it does is it uses the meta object system to generate lookups. Lookups basically are a form of cache that's also used and interpreted in JIT mode, where on first access we learn a bunch of things about the property or the ID we are looking up, and then we are storing that in a central place, and next time we come around to the same place in source code, we can look up the same thing much faster. In contrast to that, in direct mode, we just assume that all the C++ types we might need are available and can be included as headers. And we also assume that we can call getters and setters and invocable functions directly without lookups. Therefore, the generated code is faster. On the flip side, it requires access to private C++ API of all relevant Qt modules. And of course, if the type is actually only defined in plugin and has no header at all, well, then we are out of luck. So how do we enable this? First, you need to set source file properties with qml cachegen direct calls. I have an example for that too. In particular, this module here is compiled in direct mode. Then you need to link all your QML modules. Here we only link Qt Quick because we don't use anything else. You can see that here. But we don't actually link only Qt Quick, we need to link the private version of Qt Quick. Then what you should not do is generate a plugin only QML module. Because if we have only a plugin, then we cannot use we cannot link it to anything, and we cannot use its headers. Finally, you need to make sure that your generated code can find all your headers in the C++ include path. And there's something to be noted. Private Qt API changes often. So you need to recompile all your code for each new Qt version if you use direct mode. So far about that. Where are we going with this? The most important thing to be done next is increasing the coverage of the QML language. There are still a lot of things that are not supported by QML Cachegen and by the native code generation of QML Cachegen or by qmltc. For example, let and const are not supported yet, regular expressions are not there yet. Writing properties, value types and lists, because that requires write back. Then construction of value types from JavaScript objects, but yeah, okay, we're almost there with that. And then optimization of various JavaScript globals, console log most prominently. And on the qmltc side, next step is easier mixing of qmltc compiled and non-compiled mode. So we are going to build a bridge between qml component and qmltc compiled code. If you want to know more about that, the most important thing to look at is my blog series on the Qt blog. Then, of course, the documentation for Qt.qml module, QML element, and there are some coding conventions that are good to know. Okay, with that, thank you, and